An inclined plane is any flat surface that is not level. That is, that it is tipped up or tipped down. I suppose if it's tipped down, it's a declined plane, but we'll use inclined plane to cover all of them. You remember when we talked about real simple perspective, those are not vanishing points. Those should be the edge of the picture. The horizon line, it's the word horizon, which means horizon equals horizontal, which also equals level. We're assuming this line is level, that it's where the Earth kind of meets the sky. It is the horizon line, it's horizontal. Now, everything we've done just about up till this point, with a little variation last week, has had that simplicity going for it. Even when we put things in three-point perspective, and even when we spin a box on there, so that if we've got a box in one-point perspective right there, right, all those lines of that box are going to go to a point on that horizon line. If we've got one over here in two-point perspective, we're going to assume it's level, which means that all of its converging lines will converge on the horizon. It doesn't make any difference how you spin that box. Whichever way you spin it, because these are level, the lines should converge on the horizon line. In other words, we've taken this box and spun it, but we haven't tipped it yet. Well, you know that 1 point is where you're looking at it right at that angle. 2 point is anything other than that. And if you turn this into 3 point, all you've got to do is put a vanishing point down there, and all of your lines which are vertical, this one, this one, this one, this one, this one, and of course the hidden one on the other side, just point down to that vanishing point, but you're still sticking with the horizon line as your main source of the vanishing points, with one other that will go down there. But inclined planes mean that we have to leave that simplicity and get into something more complicated tonight. I want to remind you of something. We're going to use this we're going to use this level business at the end of this lecture to solve all of this other problem. When you've got it in 1 point perspective, there's 1 point and it's behind the object. As soon as you tilt it, what happens? This vanishing point starts to crawl that way, and another one comes over here from my right, over here, and crawls along, and as it goes like that, eventually it will end up there, and that one will be infinite, right, so that you'll get horizontal lines again. As you spin this, the vanishing points crawl along the horizon. Now, I'm going to use 3 examples of inclined planes. The first one, which is popular in any book, I'm going to have to violently foreshorten and violently distort the perspective to fit these vanishing points on the board. So just live with that. The first one is a rooftop. If you've got, that's your level, and you're going to build your building right here. We'll put this in 2 point rather than 1 point. Say that you've got a vanishing point there, which will make this plane of the building, and another vanishing point right here for the other plane. Remember, it's to your advantage. Let's close up that side a little bit so we can fit more. It's to your advantage to be able to draw through that, which is very easy to do in 2 point because there's only 3 kinds of lines. It's going to go off to that line. That's going to go off to that line, so you could kind of see through there like that. That's going to be what? Just vertical line. That's going to go off to that vanishing point, and that off to that, and they should meet right there. Okay, now let's put a roof on there. And it's going to rise up from the center. How do you find the center of this plane quickly? Like that, to that, and that's the center. So that means if you run a line directly up, you'll decide how steep to make it, and now do you see how easy it is to connect those dots? Now, where's that line going to go? off to the right vanishing point like so. But now we've got the problem of finding that line. Well, there's a couple ways you could do it. One, you could find the center over there and do the same thing. It's going to meet it. That's a very simple way to solve this problem. We didn't have to deal with vanishing traces at all. But what it doesn't solve is, what if there's shingles on that roof? What if we want to pull it out a little further, out here, and make it so that it overhangs a bit? But the biggest problem, if you've got shingles on that roof, you're going to have trouble with it. Now I'm going to do another one over here from a little different position. Actually, I want to use that same vanishing point. We'll give this one that we're looking down on this building the same vanishing point here. And it has to be correct for me to make this point, so I'm going to take the time of going ahead and finding all of the converging lines. And to complicate things a bit, let's say that instead of the roof rising from the middle, which was simple, let's make it rise from about right here, so it's one of those kind of strange ones that peaks up here like that. And you can go like that and connect these dots. Now, how are you going to find the one over here? You still don't have to deal with vanishing traces yet. We can still do the connect the dots thing. I'm going through all this to show you can connect dots and solve a lot of problems by going down here and then where? Off to this vanishing point like that, and if it's pointing right there, it'll intersect there, and then you'll lift up there and then run from this point off to that vanishing point, and where it touches there. You see, you solved it without any vanishing trace problem.
Can you do this from the top of the...
You could do it, yeah, that's right. You could have done it right there. Good thinking. I saved myself a few steps. Run it right across there to that vanishing point, right there, lift it straight. In other words, you're taking a ride on one of those three-line systems, and it's very simple. But still haven't solved the problem of, what if there's a bunch of shingles on here, and they're supposed to, like that angle, what do? You measure and make it equal there and measure. There's a simple way, which I'm going to get to in 10, 15 minutes. But I want to establish rooftops are inclined planes. I'll get to vanishing trace in a moment. Second problem that often comes up in these textbooks is stairways and streets in San Francisco, or a lot of European villages that have really tilted, steep streets. Now, I'm going to choose to do a stairway, and I'm going to keep it real simple because we're not going to get into the individual steps yet. I mean the stair steps. Let's put it in 2-point again. Let's say that we've got a stairway. Eye level will be, what the heck, let's put it on the same, just run this horizon line all the way along to keep the clarity. Let's say we're looking down on a stairway that would be carved out of a chunk about like this, and this would be the top and that would be the bottom. We did this before. How do you find the other side? Very easy. You run a line from there to there and then erase the lines you don't need. Okay? And somehow next week I'm going to get to, you've got to measure back how those vertical lines of that stair are going to be at one place, and how far back, and then you'll run lines off to that very simple perspective problems to run that off to that vanishing point. Well, what if this is a stairway that you're up in a New York apartment building looking down on another New York apartment building, and that's a stairway of which there are more. Above and below, they go down the side of the apartment building. What are you going to do? I know this would be impossible. You'll have to have one going like that and going like that, but I just want to make the point here, so suspend disbelief for a moment. Let's say you've got the same thing going on over here, and you've got another one. How do you know? I mean, you can't just copy that angle because these are going to they're going to look different somehow. And you don't even have to have more than one stairway to run in this point. I mean, you could, it's not in perspective. Maybe you could just do that. Yeah, we could do that. But you're going to run into a problem even if you've just got a railing. You see how that's a different angle? What if you've got a railing on the side of there? you can't just keep making parallel lines because they're going to eventually get out of perspective. In other words, you can solve a certain number of problems with this connect the dots thing, but there comes a point where this line, that point, is closer to us than this point. And this point is closer to us than this point. They are going away to the right, and they're not going to this horizon line. There's an easy way to solve it, and I'll show you. Same thing with streets as it is with stairways. But one other example. The box flap we did last week. You remember the problem with the box flap? We drew a box. And decided to put a flap on it and to make that flap hinge there, and we could have done it in any of the other ones. We just have to shift our view 90 degrees. And how do we find how it opens? We used an ellipse. I'm not going to go ahead and I'm not going to bother to go through the steps, but we had to find a big square and make it exact and find the ellipse that box top would open on, and then track that it could be like that, or like that, or like that, or like that. And then what? Off to that vanishing point. Off to that vanishing point. Off to that. Off to that. But what we didn't solve, to get the other line, where do we go? And the way I showed you, you could do another ellipse, construct that other one, do another ellipse, and it would intersect at the right point. But that was complicated. There's a much simpler way to go about it. Or let's just say that you've got a board. Somebody has placed a board. I'll make this a bit more shallow so that I don't get in too much trouble with running out of space on the chalkboard. Let's say someone has placed a board right there, and you know if it's going to hit the ground there, that line's going to go off to that vanishing point. But if it's a squared up board, you can't just run a parallel line there, because that's not going to be, this is closer to us than this. It's going away. Right? Let's make it even more severe. Let's put it at this angle. We know that we can solve that there and that there. But you know, these lines aren't necessarily correct right here. They look close enough. I'm going to show you a way to get them exact. Here is the trick of this. The vanishing trace. Let me explain what it is. When I did this horizontal here, where you can place a one-point box and any number of two-point boxes on this level plane, that is, you can spin these in any direction and be okay. They'll always be on the horizontal line. Now here's where I need your full concentration, because if you miss what I'm going to do in the next 20 seconds, you won't get anything for the rest of the evening. This horizontal line, imagine me taking this board like so and going like this. What happens to the horizontal line? It becomes a vertical line. Just like on the protractor, 90 degrees is like that. That is horizontal, that is vertical. Horizon is horizontal. One way to remember vanishing trace is usually vertical. Your horizon line becomes a vertical horizon line, as paradoxical as that sounds. Let me show you how it works. It works with a protractor. Horizontal becomes vertical. It works with the whole board. If you take this board and go like that, what is happening between this box and this box? It's tipping. Right here it isn't. It's spinning and staying level. But if I take the whole board like that, and you see what's happening, the same thing that's happening with this flap. This is simply spinning like that, but to us it is, imagine horizon line going like this, and what's going to happen? This vanishing point on that horizon line. Imagine this horizon line tipped like that becoming a vertical line like that that goes right through there, 90-degree angle. And you'll see that this is going to intersect it there, and that will become a new vanishing point for any line parallel to that. What's the line we're trying to find parallel to that? The one that comes from the other hinge over here. And this one is going where? Away from us where? Down, which means it will hit a point there, which means if we want to find that other flap, it will intersect there, and we can find the hidden flap. This line is going where? Closest to us, furthest away. Don't try to bring it the other way. This is closer to us. It's going away to our right and down, which means it's going to hit a point there. Any line parallel with that will hit a point there. What line is parallel with that? This one we're trying to find over there. Do you get the idea? What about this one? It's just going to stay vertical because it's not going away from us. And so you just simply draw a line like that. This is called a vanishing trace. It works to quickly find the missing line in the box flaps. If you want to get it, think like this. Take this, what's going on, so complicated, and go like this. Watch me, those of you looking at you, go like this. And you'll see that all these are doing is crawling along a horizon line that we've tilted at 90 degrees. Let's go back over to the rooftop. There's the horizon line. Everything level points to that, but these aren't level. So what do? 90 degrees through there. Where is this one is closer to us than that one, correct? So that means it's going away, which means anything parallel to that, got to fix that. That line over there should go over to there. Now, how about this one? That's closer to us than that. It will land right about there, which means this one will land right about there. Vertical land. So let's try it on this one. We've got level, and we know it lands right there. If this is going down, what about this one? It should, we've got to correct it now. I was not accurate enough. This is going up. They've got new vanishing points. All it's done, remember, think of it as a box flap. And this is the hinge. It was pointing there, and then it went like that, and as it goes, it just crawls up the top. Just like as you spin these boxes, they crawl along the horizon line. Is it making sense? We'll take one more example. Take this stairway. We know that the level part of this stairway converges at that vanishing point. Let's make sure you can see this clearly. And this is also level. That line is level, and that line is level, and it converges at that vanishing point. So it makes sense that if we run a line vertical, horizon to vanishing trace, VT vertical, 90-degree line, that if that hits there, then this is parallel with it and will converge there also, and so will this one, and so will this one, and that will go off to there. And if you want to put a railing on here, you start, where do you want that railing to start? Right there? Go right up to that vanishing point and run a straight line down, and that's where that, and how do you do this one? You can measure the vertical. Run a straight line off to that vanishing point. It's a new vanishing point, the vanishing trace. Now, all of these principles about if you pull in the 2 points tighter, you get a more wide-angle effect. At least you do left to right. If you pull these in tighter, you'll get a more wide-angle effect like this. pulling them in left to right, you get a more wide angle effect. Like you're distorting space like this. Doing it vertically, you're distorting space like that and looking through a fisheye like that. The 1 point business, this is in 1 point. If that was the plane of a box, it would converge right there and it would be in 1 point. Because that is not going to, actually it would be in 2 point, because there'd be a kind of a 3 point thing going down. As it's going down, you tilt it like that, it would be going down to that vanishing point. But the thing is, the same principles apply. All I've done is taken a big chunk out of this chalkboard and gone like that and turned this horizon line into a vertical line. And that is the big trick of how to do rooftops and stairways and inclined streets in San Francisco and box flaps opening and closing. Now, I'm going to review it one more time to let you know if you've got a problem with an inclined plane, here's how you figure it out. 3 questions. Look at any line that you're trying to figure out, this one, and say, where is it going? It's going away to the left. Is it level? Yes, that line's level. Is it level? Yes, it's level. If you wanted to find the shadow in direct sunlight, where is it going? Off to our right. Is it level? Yes, it is. Now, what about this line? Ask, where is it going? It is going away from me from there to my right and up. Okay, that's the first question. Ask, where is it going? Away to my right and up. Then the next question is, where would its vanishing point be if it were level? Where would this vanishing point be if it were level? Sometimes you have to go to the pivot, right, and say, oh, go be right there, and that's what I've done actually, should be right there. Where would it be if it were level? And then the next thing you do is you trace up, or if it's going down, trace down on an imaginary or literal vertical line and find where it hits. And if it hits every line that's parallel to that, which would be this line, will disappear there. So you ask, where is it going? Away to my left and down? Where's one that's going away to my left and down? Away to my left and down. Ask, where is it going? And then, where would its vanishing point be if it were level? If it were level, its vanishing point would be there. Then, third thing, trace down and see where it hits 90 vertical line there, and then the other one's parallel to it will land at that point. Now, all I've solved is inclined planes. If you are doing stairways or roofs or box flaps, you can run into a lot of other problems. What if there are shingles on this roof? Well, I've solved the problem of the line, the angle of the line for how those shingles are going to fall, which is a big problem when you're trying to divide up that space. You can't just do it with a set of calipers. But I haven't solved the problem of how much bigger these bricks look compared to these ones as they go away to my right. Or, what if this building is made out of bricks? How do we know, I mean, if the bricks are all of the same width, how do we know how much smaller they get as they go away? These stairs, how do I know? I mean, I know that as they go away from me, they're going to get a little closer. I've got to mark off, but how much closer? And the same thing goes for floor tiles and ceiling lights and rows of chairs and piano keys and anything where you've got increments. If you've got rivets on the side of this building, if you've got a picket fence that's going back, how do you know how much closer those poles get to each other as they go back? That's what we're going to deal with for the next 2 weeks, which is measuring things back into space. I'm going to give you 5 ways to do it. 3 next week, to the following week. 5 ways to measure back in space. And then when you've got your big shape for the inclined plane of these stairways, I'm going to show you how you can simply make a line, and this will be a couple weeks from now, and divide up that stairway any way you want, throw it back to a vanishing point, run lines to that vanishing point, see where they intersect, and make exactly 6 or 8 or 11 or 14 or 3 divisions that will go back in space correctly. So that you can then run those lines up and see that will be the top of the stairs, and then you can find where the tread goes and run it up there and start connecting the dots. 3 weeks from now, you should be able to solve any perspective problem. Theoretically. Okay, the first question is, where is it going? Away, to the left, right, and up or down. The second question is, where would its vanishing point be if it were level? You may have to find the pivot point for that. And then the third thing, well, I'm sorry, the third thing is not a question. Did I say it was a question? I guess I did. The third thing is an action. You need to then trace vertically, up or down, from where that vanishing point is and find the new vanishing point. Where it intersects, where your line intersects that new vanishing trace will be your new vanishing point. Now, you want this to stick with you? You ready for the pitch that you get every week? You want this to stick with you? Open up the books this week and read those chapters. And take your time with them because they are tough. I've been through them and I know my eyes start to hurt looking for little letters and trying to keep my finger on. It helps to have a pencil. Keep your finger on the text while you're looking for those little letters so that you can go right back to where you're reading. But if you'll do that this week and review all this stuff in those books with all those great illustrations to make the point, The House of the Seven Vanishing Points and the stairways and the streets in Ernest Watson's book, then you'll be able to look at one of these desks, and if you practice this, say it's like that, and just kind of imagine that, and you'll get a better line even if you don't plot your vanishing point, just because you'll kind of know theoretically what's going on there.